So what I'm going to do right now is use calculus to derive the formula for the arc length of a segment of a polar function. So right now, this right here is going to be our polar graph. And we want to find the arc length from here to here. And the easiest way to do this is to first find a formula for the arc length between two polar coordinates that have an extremely small change in theta, and then use that to find the arc length of the polar segment that we have. So right now we're going to use this small portion of the segment that we have, and it's going to be that. And we're going to right now focus on trying to find a formula for the distance between these 2 points. And we're going to pretend that this is an extremely small change in theta. So the distance we're going to find is going to be represented by this green line right here, which we're going to call A. And so the easiest way to go about doing this is by simply using the Pythagorean theorem. Right here we can make a right triangle so that this is the change in x between our two polar coordinates, and that's the change in y. So A is just the square root of the change of x squared plus change in y squared. The problem with this is that x and y are Cartesian descriptions and we're working in polar, so we're going to have to convert that entire thing to polar. So we know from previous calculus problems that the change in y, which can also be written as dy d theta, is equal to dr d theta sine theta plus r cosine theta, and that the change in x, which is also written as dr d theta, dx d theta, can also be written in polar as dr d theta cosine theta minus r sine theta. And so since we're trying to convert this whole equation to polar, we can just substitute this for all of this, and the same thing with the change in x into that original formula. Okay, so after a whole bunch of foiling and algebra, you get this whole nasty equation for our original arc length equation for small differences with small changes in theta. It turns out to be this. So these two parts cancel out because they're opposite signs, and yeah. After still more algebra, that equation eventually simplifies to this. Sine squared theta and since we know that sine squared theta plus cosine squared theta equals 1, then we eventually get this really nice equation, which is dr d theta squared plus r squared. And what this equation is in polar, the distance between any 2 points, and we can use that to find our arc length of our original function. Because we used the formula with two polar points with extremely small changes in theta, we can say that for every small change in theta, the arc length is the square root of d theta squared plus r squared. And so we can apply this to our larger equation by summing this original equation up for every small change in theta. And to do that, we use an integral. So this means that for the arc length of our original equation, we get arc length equals the integral of the square root of dr squared d theta plus r squared all times d theta from a to b. And a and b are just the original limits for the segment that you want to find the arc length of for your original polar equation. So since we're using integrals, and integrals are by nature approximations, there is a small amount of error. And as you can see in our drawing, we have error here. But since this is an extremely small change in theta, our error becomes so infinitely small that it is so unfathomably close to zero that the error is negligible. So we just get this as our final equation, and that's the arc length.